Okay, so last time we were talking about filters, and I sort of talked about low pass filters, high pass filters, notch filters, or band pass filters, which basically can be thought of as a combination between high pass and low pass filters. And I sort of introduced the idea of frequency response, body plots, transfer functions, just introductions, right? So that's what we did last time, and we went through this slide, and we sort of looked at what happened to the original signal, and we said that it's sort of like a low pass filter. It's the high frequency content of the signal. If the high frequency content was indicating the presence of these two, at the output of the filter, I don't see them. So it looks like this filter removed the high frequency content and as well as scaled down the high frequency content, and it also amplified the low frequency content. That's what this filter did, right? So that's what we talked about last time. We'll continue, and we'll do some examples and continue what we were doing last time, really. So here I have and we said that these filter, and we also said that the phase shift of this signal changed as well, right? So the peak here, there's a line that goes all the way up here. This line goes to the peak of this waveform, but the peak of this waveform is shifted from where this line is, right? So the peak is a bit shifted as well. So in the output, right? So we said that these filters cause a magnitude shift as well as a phase shift because they're complex numbers, right? It's an AC quantity, it's a complex number. Any AC quantity can be represented as a phasor. A phasor can be projected on the real and imaginary planes, right? So any AC quantity is basically a complex number. So there's an accompanying magnitude and phase shift with that. So we said that these transfer functions typically have an effect on magnitude and phase. So here they give us an example of a transfer function. So where I have, remember what we said we're doing, I can represent what we're doing as an input signal coming in to some transfer function, and then output signal coming out. So this is V in and V out, or it can be I in and I out, or it can be V in and I out, right? It depends on what transfer function is between any two variables in your system. So for simplicity, we'll just talk about V in and V out. So a signal is coming in and something else is coming out based on the transfer function. So this is the transfer function of h of f. So this is frequency, this is the frequency axis, and this is magnitude, and this is phase angle of this h of f, right? So what is the magnitude doing? What is the magnitude plot doing? At low frequencies, or at DC, whatever is coming in is multiplied by 4. And as we increase the frequency up to 2.5 kilohertz, it's being scaled down linearly, right? And at 2.5 kilohertz, anything that is beyond 2.5 kilohertz is multiplied by 0, right? It's the gain, or the gain of this transfer function is 0. So the signal comes in, it's multiplied by this transfer function. This transfer function acts on the signal, so it's multiplied by 0 as a magnitude. And then the phase shift does something else. So this is what's happening to the gain of the signal, the magnitude of the signal that's coming in. And the phase shift of the signal that's coming in is changed according to the phase shift plot of the transfer function. Right? So what's happening here? As you increase the frequency, the phase shift of this transfer function changes. So you have a signal coming in. Let's say this is V1 angle theta. It's coming into this h of f. This h of f is acting upon this signal. So it's changing this signal. You have the signal that is acted upon by a transfer function, meaning it's modified by that transfer function. So you have a complex number and another complex number that's affecting. We said we're going to multiply the gain of whatever's coming in by 4 to look at the magnitude plot. And we do the same. We're basically taking the input signal V1 angle theta, and multiplying it by h as a magnitude and angle as a function of frequency. Right? So you have and then the output is this V out. Right? So if my for me to find out what the output will be, I take my V1 multiplied by h as a magnitude. Right? So this is my new magnitude. How about my new phase angle at a specific frequency? It's theta, which is the angle of the input, plus, right? You're multiplying two complex numbers, so you multiply the magnitudes and you add the angles if they're. So you add the angle, so it's plus theta f. F meaning it depends on frequency. So because at every frequency, that angle is different. At every frequency, the angle is different of that transfer function. Like here, at every frequency, the angle, the magnitude is different. Right? So here I should have written h of f here, for example, right? Because at every frequency, the magnitude is different, and every frequency, the angle is different for a transfer function. Right? And that's what the transfer function does. Right? It changes the magnitude and frequency of the input, magnitude and phase shift of the input, depending on the frequency of the applied signal. Right? So you have a transfer function. Again, your car. Depending on how fast you press the accelerator, the car will respond differently. But it's the same car. Right? So it's the same transfer function, but it responds differently for different frequencies of the input. Right? That's what we have. So we have an input 2 cosine 2000t. Remember, this is 2 pi f t. This is omega t. Right? This is omega t plus some phase shift. So if I would like to represent this in phasor form, so I know that the frequency that we're talking about is 1000 hertz, right? So 2 pi f, so it's 2 times 1000, and I have pi here. So the frequency of interest of this signal is 1000 hertz, right? So then the interesting magnitude and phase that I'm looking at are the ones that are occurring at 1000 hertz, right? So the signal is coming in. I can rewrite the signal in phasor form, right? It's already in cosine, right? So this has a magnitude of 2 and an angle of 40 degrees, right? In phasor form, it has a magnitude of 2 and an angle of 40 degrees. And it's at a frequency of 1000 hertz, right? So this signal is going into this block. So it's being processed by this block. The signal, this data coming in is going to be processed by this block. This block will be multiplied by that signal. So I have 2 angle 40, and my transfer function of interest is coming from this plot at 1000 hertz, because the frequency of the signal is 1000 hertz. So I have to go and see what the magnitude response of this transfer function at 1000 hertz. So the magnitude response is 3. What does that mean? It means that any signal coming in, its magnitude will be multiplied by 3. How about phase? This transfer function causes a phase shift of 30 degrees to any signal coming in. Right? So any signal coming in will be phase shifted by 30 degrees at 1000 hertz. So my transfer function was, my magnitude was 2. I would have to take the magnitude and multiply it by 3. Right? So my transfer function has a magnitude of 3 and a phase shift at 1000 hertz of 30 degrees. Yes? Yes? You will either have the graphs or you will have the transfer function written and you plot the graphs. And we will see how we do that next. Yeah, it's either this or that. Either the equations of this or the picture, basically. So, what is V output? V output is the magnitudes multiplied by each other, and the magnitude and you multiply the transfer function at 1000 hertz with your input signal. So, because it's in phasor form, it's 3 angle 30, which is my transfer function, multiplied by 2 angle 40, which is my input signal. So you're gonna multiply 2 by 3 and add the angle, so it's 6 angle 70 degrees. And I can take this and rewrite it in the time domain as 6 cosine 2000 pi t plus 70 degrees, right? So converting between phasor domain and time domain. So any questions on this? Yes. 1000 because this is omega t, right? This is omega. This is 2 pi f. So this is 2000. So the frequency f is 1000. So I need to. So the signal coming in is 1000. So I want to see how my transfer function will respond at 1000 hertz only. Yeah, the specific frequency is there. And think of the car, right? The car is there. The car will respond to anybody pressing the accelerator at any speed. Whatever, how fast you can respond or how fast you can put the accelerator is you. That's your input, right? The car will not change. It has a transfer function. For somebody that's slow, it will respond in a certain way. For somebody that's fast, it will respond in a certain way. That's the transfer function of the car. It will not change. So it will know, you know from the beginning that if you're going to press fast, you know that the car will know that, okay, this is somebody pressing fast, so I have to respond in whatever way that, at whatever frequency that the person or the input signal is coming in at. Okay? Any questions? Okay, if you get this, then the rest is pretty easy. So the next example I think is, okay, so now I have, two signals coming in, right? Think of what we did initially. Any signal is composed of its, a bunch of sinusoids or cosinusoids, and I can take each one and apply it separately. So if I get a square wave, the square wave is a bunch of sine waves. If I take a square wave, put it through a transfer function, what would be the output? I will do a Fourier series, for example, take each one of these components and see what the effect of each one is after it passes through this transfer function, and add them up at the end, right? So you can do the same here. Here I have three signals. I have 3 plus something at 1000 hertz plus something at 2000 hertz, right? So how will this transfer function affect this one? This is what? 3 is DC, right? It's not a sine wave. It's a DC signal, so it's at 0 hertz, right? So the magnitude will be multiplied by what? The magnitude will be multiplied by what for this 3, for the DC, for any DC signal? Look here, not at me. Exactly. So the again, you go to whatever the frequency of the signal is. This is a DC signal, so you go to 0 hertz. The magnitude will be multiplied by 4. How about the phase shift? 0. So this filter does not affect the phase angle of a DC signal, and it multiplies and the gain for a DC is 4, right? And at 1000 hertz, the gain is 3, and the phase shift is 30 degrees. At 2000 hertz, the gain is 2, and the phase shift is 60 degrees. Okay, so the solution is in the next slide. This is put here very systematically, right? So I have my input waveform are chopped up into 3. So V input 1, V input 2, V input 3. This is at 0 hertz, 1000, 2000 hertz. So I have to look at my transfer function at 0 hertz, 1000 hertz, 2000 hertz. What is my transfer function at 0 hertz? It's just a gain of 4. What is my transfer function at 1000 hertz? It's 3, gain of 3, and a phase shift angle of 30 degrees. So it's 3 angle 30. 2000, it's 2 angle 60 degrees, right? And then you take each one of these signals and multiply by the corresponding transfer function at its specific frequency, right? So you take 3 multiplied by h of 0, 2 angle 0, right? The phase shift of this is 0, multiplied by 3 angle 30. 1 angle minus 70 degrees multiplied by 2 angle 60 degrees, right? And that's what they did here. So with a 3, and then 3 angle 30, which was my transfer function at 1000 hertz, multiplied by 2 angle 0, and then 2 angle 60, which is my transfer function at 2000 hertz, with 1 angle minus 70 degrees, so you get 2 angle minus 10. Right? So this is the output in phasor form. You can write each of these back in time domain as a set of cosines, right? And then you can write the composite output at the end. Everybody's okay with this? So special cases, so this is really what we need to know. A special case is things that we want to memorize now, right? I mean, not memorize, or things that we will, okay, we've designed, pre-designed for you. We know that designing a low-pass filter is interesting. We know that designing a high-pass filter is interesting, and we know that designing a notch filter is interesting. We will not cover notch filters because it's a cascade between the signal comes into, let's say, a low-pass and then a high-pass filter. We talked about that. So it's gonna, whatever comes in will be go through a low-pass filter first, so you will do this same trick we just did. So the objective now is to find this H, or the transfer function, for a low-pass filter and for a high-pass filter. Be able to draw these magnitude and phase plots. If we draw the magnitude and phase plots for a low-pass filter and a high-pass filter, that's it, we're done. So now we are not going to learn anything new. We are going to apply what we did, but on a specific transfer function that is interesting to us, which is for a low-pass filter and a high-pass filter. And we're going to see how to construct a circuit to make this happen, right? So this transfer function at the end of the day is a circuit. So what does this circuit look like that allows you to draw a magnitude plot like this, like a low-pass filter, and a phase plot like a low-pass filter, and a magnitude plot like a high-pass filter? What does this circuit look like? That's what we're going to look at here. So when we talked about low-pass filters, so low-pass filters, what they do is allow low-frequency components to pass, and then attenuate high-frequency components. And we said last time, so we're going to only study what is called first-order low-pass filters. What I mean by that is first-order meaning there's only one energy storage element. So the order of an electrical circuit is typically tied to how many energy storage elements you have in the system. Right? When you study control, I will not say Dr. Muhammad Nuno because Sally will laugh, but the order of a electrical system will depend on, because again, each of these energy storage elements is what affects the time domain change of the system. So resistors don't have any dependence of time, right? You put voltage, you get current that looks exactly the same. Inductors and capacitors, there's a time domain dependence of voltage and current through and across. L is equal to di by the, VL is equal to L di by dt in an inductor. IC is equal to C dVc by dt. So there's a time has a factor in what voltage and current appear across and through a capacitor and an inductor. So these components are what changes the performance of the system with time. Because remember, we're looking at input versus output voltage, the ratio of output versus input at every frequency, meaning time domain performance of the signal is important, right? So anytime we have one capacitor in the filter, it's called a first order filter. We will not study high order filters here, but I will tell you briefly what the difference is. So with a first order filter, we said that for a low pass filter, I will show you why this is a low pass filter, but for a low pass filter, we said that we would like the input to have a gain of, let's say, 1, magnitude, okay? And we would like the high frequency, at all the high frequency components to be attenuated, right? So we would like at high frequency to be able to do something like this. So everything this is frequency. So between here and here, okay, or between the change from being sort of just a unity gain to 0, I can go this way, or I can go this way, or I can go this way, right? There's infinite possibilities to go from here to here. That will depend on the order of the filter. A first order filter does not have a very sharp response. First order filter is a cheap solution. It just uses a single capacitor. So the transition between, pass band, this is called pass band. The transition between the pass band and attenuation will take time. It will take, there's a certain amount of frequencies that it will let through. It will keep attenuating frequencies. Between here and here, the signal is being attenuated, but you will still see some content at, let's say this is 10 and this is 100. So 50 hertz, you will still see a 50 hertz signal. If you look at the output, you will still see a 50 hertz signal, but small. If the input has a 50 hertz signal, it's not going to be the same as at the output, because it's not multiplied by 1 anymore. It's multiplied by something less, like half. Right? It will still exist, right? But it will be much smaller. So if you don't accept that, then you want a higher order filter, right? So it's just a more complicated filter. Okay? And we have topologies for these. Like we have this for the low pass filter. Like this is what a low pass filter, single first order low pass filter looks like. We also derive circuits for second order, third order, fourth order, etc., etc. Right? So it's not something that's not something we invent. People know how to design these things. Okay, so let's go back to here. So I will show you why this is a low pass filter now, but I just wanted to talk about this idea of a first order, and then okay. Before we go to an equation that you will have in your equation sheet, I would like to define that. So remember, our objective is to find h as a function of frequency for this circuit. If we do that, then it's the same as what we did with the examples before. That's it. And we're going to do that for the low pass filter and high pass filter. So the derivation is not something I'm asking you to know, but I think it's good for you to sort of know why this is h for the low pass filter. We said that for a low pass filter, we said that the frequency response, or the transfer function of a system, h of omega t, or h of f, is equal to what? The ratio of the output voltage to the input voltage at each specific frequency. So output is equal to V out as a function of frequency and over Vin as a function of frequency. Right? So I would like to find, so my Vin is Vin. I just have one source, and it will be at a certain frequency, right? So I need to find V out. How do I find V out? Here. What is V out equal to? It's a circuit, right? It's a circuit. So I can find the current, I, and if I take I multiplied by this impedance, then I have V out. Or I can use Kirchhoff voltage law, take Vin multiplied by this impedance, and then divided by the sum of the two impedances, right? So if I go the route that calculate the current route, so I is equal to what? Vin, which is the input voltage, divided by, as a phasor of course, because since it's an AC signal, so this will have a magnitude and an angle, divided by what? R plus 1 over J omega c, or 2 pi fc. Right? So this is the current. How about the voltage at the output? Will be this current multiplied by the impedance. Right? So I take this current multiplied by the impedance. So I have V out is equal to 1 over J omega c multiplied by V in over R plus 1 over J omega c. So I end up with V in over J omega RC plus 1, right? This is V out. My transfer function is V out over V in. So I bring V in here, so the transfer function is 1 over 1 plus j omega RC, correct? This is a complex number. This is my H now. This is my H of omega or H of f, right? So this is a complex number that has a magnitude and an angle. The magnitude is equal to what? These are two complex numbers divided by each other, right? So the magnitude of the top is equal to magnitude of any complex number. Magnitude of the top is equal to 1, right? Magnitude of the bottom is equal to square root of this square plus this square. Square root of 1 squared plus j omega r c squared. That's the magnitude of this. How about the phase angle? Phase angle is equal to what? Angle. Angle of the top is 0, right? This is a real number. And then it's a division, right? So I'm going to subtract, right? So angle of the bottom is inverse tan, right? The complex, the imaginary over the real part, right? Correct? So inverse tan, what? Omega RC, omega inverse tan omega RC, correct? And what we do is, they actually give this a name, sorry. So they call this 2 pi or omega RC, they call it FB. They call this the 2 pi RC, they call this FB or break frequency. They give this a name of the break frequency. And, or sorry, so they call, not omega RC, they call, so this is 2 pi FRC. So they call the 2 pi RC, they call it FB. Or 1 over 2 pi, sorry, FB is equal to 1 over 2 pi RC. Okay, so they call this 1 over 2 pi RC FB. So how do I rewrite this? Sorry, as 1 over 1 plus J what? F on top, and then 1 over, this is 1 over FB basically, right? Because FB is 1 over 2 pi RC. So I have a 2 pi RC here, so it's like flipping FB. Are you okay? Yes, so this is F over FB. Right, guys? FB is, okay, so FB is 1 over 2 pi RC. So 1 over FB is what? 1 over FB is 2 pi RC. 1 over FB is 2 pi RC. Here I have 1 over 1 plus J 2 pi FRC. So let's keep the F outside. Keep the F outside. And then 1 over FB is 2 pi RC. Right? So that's what this is. Sorry, okay. So that now let's rewrite the magnitude and phase of this again. The magnitude of this is again 1 over the magnitude of the bottom. The bottom magnitude is square root of 1 plus F over FB squared. Correct? That's the magnitude. How about the phase shift? It's 0. It's minus inverse tan F over FB over 1, right? So it's F over FB. Everybody's okay with this? Yes? No? So we've come up with now the magnitude and the angle of this transfer function. You don't need to know the derivation, right? But before I didn't want to go to the next slide where we show the magnitude and angle without showing you the proof. Okay, so The magnitude is 1 over the square root of f over, yes ma'am. They just called it, they just called it that. Okay? So they just called it that. You can keep it. It just simplifies because it has some significance in the body plot. So that's why they call it FB. Right? So everybody's okay with how we transition from here to here? So it's basically Kirchhoff voltage law. And we do the same, and we're going to do the same for a high pass filter. Exactly the same. So now we have what we need, right? We have the magnitude and angle of my transfer function. And I can just substitute with frequencies and whichever R and C values that I have in my circuit to draw the magnitude and phase plots. Right? This just happens to be the magnitude and phase plots for this in terms of FB. FB basically contains your R and C values. Right? This is your design. This is your design circuit is depending on your FB term. So just what the only significance of FB is that at FB the magnitude becomes 0.707 and FB at the phase becomes minus 45. If you substitute with put F equals to FB, these cancel, then the magnitude F equals to FB, so this is 1, so it's 1 over square root of 2, so it's 0.707. Right? It has some significance for you to know, okay, certain numbers that happen at the break frequency. So because you typically want to do what? You typically want your magnitude, remember, you want your magnitude, let's say your low pass filtering. You want the input signal to be at high frequency scaled down, right? That's what you want to do with the low pass filter. So at a certain frequency, so that is, for example, FB, you know that the signal will be scaled down by 0.707. So FB is typically a sort of like your break frequency, meaning before FB is your pass band. So before FB, everything will pass with a high magnitude. After FB, the magnitude of the signal is attenuated considerably. That's significant. No, the break frequency is only a single number. Remember, FB is 1 over 2 pi RC. R and C are something that you select and build. I mean, this is what you build your circuit with. So you select and build the circuit, so you only have one FB for any circuit you design. No. 2 FB is no, FB is just a number. FB is just a number, right? But typically you design, typically for example, you have this, I hate this thing, right? I really hate it, right? So this thing keeps humming at a certain frequency, right? I would like to not hear this humming. So so for example, this is probably a higher frequency. This is probably a high frequency. It's not a low frequency noise. So I would like to, in that case, I'm going to a high pass filter, but it's okay. It's the same concept. So there's an FB concept as well in a high pass filter. What do I want to do? I want to attenuate this at high frequencies. So actually, it's still low pass filter. So I want to attenuate this at high frequency. So what do? I want the gain at high frequency to go very low. If this is 1,000 hertz, this thing I'm hearing is 1,000 hertz, right? I want 1,000 hertz to be 0. I don't want to hear it at all, right? So I will make FB closer to what? Maybe 10 hertz. So that 1,000 is up here, completely attenuated, right? But if I make my FB 900 hertz, then I know at 900 hertz is when I start attenuating the signal. That means at 1,000, which is where this thing is, I will still hear it, right? Because it's not attenuated very quickly. Because of this is a first order filter. The attenuation response of the first order filter is pretty slow. Okay. So I would probably choose FB in this case. If this was 1,000 hertz, I want to eliminate it. I would choose it at least 10 times less. For example, if I'm using a first order filter. So then you know FB. Once you know FB, you can go and select an R and a C. That's how you design your filter. Okay. So they sort of apply some of the stuff we just did. Some of the stuff we did in the previous examples is sort of applied here on the low pass filter. So we said that we know that at frequency equal to 0, if we look at our magnitude plot, I know that the magnitude is pretty much 1. Whatever comes in at DC at 1 hertz, 5 hertz, it's going to go out with the same magnitude almost. So at f of close to 0, h of f is equal to, as a magnitude, will be 1. And the phase will also not change. Right? When f is close to fb, around f is equal to fb, the magnitude is close to 1 over square root of 2, and the angle is close to minus 45 degrees. And when fb is very large, the magnitude will go down to 0. If you go look at the magnitude, fb is very large, right? So if if f is very large, that means this is 1 over a very large number, which is 0. So at the magnitude will go to 0 at very large frequency. And the phase shift will go to minus 90 degrees. That's what this filter does. Any questions? Basically, it's what we did in the previous examples, but with some new names to it. The break, this FB is the break frequency, for example, of that filter. We talked about pass band, block band, or attenuation band. Okay. So here's exactly what we did before, but applied to a low pass filter example. So you have your input signal is a set of cosines at 10 hertz, 100 hertz, and 1000 hertz. Right? So 10, 100, and 1000 hertz. Is applied to an RC low pass filter. Find an expression for the output signal. FB happens to be 100 hertz. Right? FB happens to be 100 hertz for that specific filter that was designed. Okay, so FB for that filter that we selected was 100 hertz. We're still not done, right? So 11:40. So FB that was selected was 100 hertz, right? So now I'd like to go in and see what's happening to the rest of my signal. So I do the same thing. I take first signal is 5 cosine 20 pi t. So I can write it in as phasor form as 5 angle 0, and the frequency of this is 10 hertz, right? I look at how the filter will affect it. So at 100 hertz, at f is equal to so at 100 hertz, my h of f is certain value. So this is my transfer function at 100 hertz. Like why are they multiplying it by? Yeah, they're just here. 100 hertz is your break frequency, but then they change this to 100. So they're looking at V2 actually. There's a mistake here. You see why there's a mistake? So because they took the transfer function, they took your h of f at 100 hertz. Fine, this is my transfer function of my filter at f is 10 hertz. Very confusing. Yeah, sorry, no, there's no mistake. So remember, 1 over 1 plus j f over fb. F is what? F is the frequency of the input signal. Input signal is at, this is 2 pi f. This is 2 pi. So this is, so f is, in this case, is 10 hertz. So f over fb. Fb is your designed filter. Fb happens to be 100 hertz in this case. So 1 over so and so. So this is your transfer function of the signal. They should have put here 10. So h of 10 is equal to 0.995 with this angle. So this is your h now, and then you already know your signal. So you multiply the magnitudes, add the angles. So it's 4.975, angle minus 5.71. Right? So any questions about this? And it's exactly the same example here. So, but they apply it for f is equal to 100 now. So 100 over 100 would equal 1. So the magnitude obviously changes, and so does the angle in this case. So, any questions about this example? Now that we have h as a magnitude and angle, it's the same as what we did before. You okay with this? So, and the same thing applies to the high-pass filter. A high-pass filter, if you design a high-pass filter, one version of it can be this circuit here. Remember, what does the capacitor look like for high frequency? Or what does the capacitor look like at steady state for DC? DC. Remember, what's the impedance of the capacitor? The impedance of the capacitor is 1 over j omega c, right? So if omega is 0, so DC, right, what does the capacitor look like? 1 over 0, infinity. So it's open circuit. And 1 over omega big is 0. So at high frequencies, the capacitor is short circuit. At low frequencies or DC, capacitor is an open circuit. So at high frequency, what is this capacitor doing? It's letting everything go through, right? So it's a high-pass filter, right? It's a short circuit to high frequency. And at DC, what is it doing? It's blocking. It's an open circuit for any DC signal, right? So that's where the circuit comes from. And then to find the transfer function, we do the exact same thing. We look at V out over V in, right? The derivation, I'm not asking you to know, but it's similar. You find the current, and then after you find the current, multiply by the resistance, and this is V out. V out over V in will be the transfer function. What does this transfer function look like for a high-pass filter? This is what it looks like for the high-pass filter. It's a complex number that has a magnitude and an angle. So I know the magnitude and angle of my transfer function in this case. As expected, this transfer function at high frequencies will allow the signal to go through and will not attenuate it. Right? The attenuation or the gain is 1 at high frequency. At low frequencies, it's blocking all these signals, attenuating the signal. And the phase will have some phase response. Okay? And then we repeat the same thing like we did for the low pass filter. So they go through and talk about the asymptotes. At f is 0, what's happening? The magnitude is 0. At high frequencies, the magnitude is close to 1. Between them, magnitude is at a certain value and a phase is a certain value, right? And then, so that's a high-pass filter. There's no example of that. Something to note here, okay? If you look at the way this is drawn, it's drawn versus frequency, right? But it seems, this is a linear scale for frequency, a linear scale for magnitude. When you look at this, you don't think that you're only, you want to make, let's say you want to look at 100 times FB or 1,000 times FB. You're not going to draw and extend this scale forever, right? It's going to be a very big figure, right? So if you use a logarithmic scale, then you can shrink down the figure considerably, right? So, and basically that's what the next section is, taking these figures, magnitude and phase figures that are drawn using linear scales, and then converting it to a logarithmic scale, right? So how do we do that? And that's called a body plot. So you will take your magnitude and multiply it by 20 and take the natural log 10 or natural log of that, log base 10 of that, sorry. So you take log base 10 of the magnitude and multiply it by 20, and that's how you will convert your signal to logarithmic scale. Right? And you can do the same on the frequency plot. And typically we are interested in, for example, we can do the same on the frequency plot, and we're typically interested in, for example, FB, for example, or frequency of a signal, and 10 times that, for example, or 2 times that. So we give that a name, right? We give, if there's a 10 order of magnitude difference, we call that a decade. And if there's a 2 order of magnitude difference in frequency, we call that an octave. Why is that interesting? Because typically our magnitude, remember, for a high-pass filter, what is it doing? At low frequency, it's attenuated at high frequency, it's passing, right? From this low frequency to high frequency, there is this slope, right? This slope is a certain value. It's not changing in slope, right? It's just a continuous slope for a specific RC circuit. So this slope, we have to give it a name, or we have to sort of quantify it. And we typically quantify it in terms of dB or decibels per decade. So when we multiply by 20 and take the log base 10 of the magnitude, it's converted to units of decibels. So it's converted to units of decibels, and we typically quantify the slope of the signal as dB per decade or dB per octave. Just to give you an idea of what dB, what is 10 dB, 20 dB or something, I have a link here that talks about transformers. Have you ever, have you ever driven by or walked by a big transformer, for example, in your neighborhood, or these small buildings around your neighborhoods that have electrical equipment in them? So they basically have a big transformer inside. Have you ever heard noise? You will hear a hissing noise. Or if you did an internship and you passed by a transformer, in a Rasgas or Qatar Gas, one of these places, you will hear a small, a hissing noise. This transformer noise, of course, you don't want it to be very, very loud, so there's a specification for it. So just to give you an idea, so even these largest transformers, the noise is the level of that noise is about 64 dB, about 60 dB. So if it's something you can hear, it's about 60 dB. So what does that mean? It means if you want to attenuate even further, right, you have to you have to find a way to attenuate the magnitude of this signal if you don't want to hear it. Like if I don't want to hear this, then at that frequency, I want to make sure that the transfer function of my filter will make the gain minus 100 dB, for example, if I really don't want to hear it. Right? I just wanted to give you an idea of dB and how it relates to noise. Okay? So we'll stop here, and basically next time we'll wrap up this chapter. So basically, the only thing left is converting these plots to Bode plots, multiplying by these gains, meaning redrawing everything in log plot basically. So we'll do that next time.